Hi, my name is Alex, and today I'll be talking about my project called Live Captions. So I worked on this project as part of the 3-month fellowship program that FUTO is offering. It's been a great experience. I got a lot of work done during the 3 months. And applications for the next round are open at the time of this video if anyone is interested in working on open source software and projects like this that help people. So to talk about my project, I'll first talk about the problem that it solves. So there's some people in the world that need captions. For example, people with hearing disabilities, there's also people who just prefer watching videos with captions, especially in the younger generation. But not every situation has, the possibility of having captions. Some videos don't have captions. If you're in a voice call or a Zoom meeting, there's no captions there unless, the program provides one for you. And there are already solutions for this. For example, there's a solution integrated into iPhone. There's one in Windows 11, Android on some stock firmware on some phones. But these are all proprietary. No one knows how they work. You don't know where your data is going. Some of them make the promise that, your data stays locally. But, you would have to really read through their privacy policy and be completely sure of that. And as for open source solutions, they were really falling behind. There was nothing really like this for Linux. And, I think no human being should be subject to Windows 11 or having to choose between having live captions or using a free operating system. I don't think anyone should have to compromise on software freedom just for this feature. So to fix this, I decided I would develop an open source live speech recognition library, train some public models, and build a Linux application that neatly wraps all this in a nice package. And that is what I built. So this application is available today on FlatHub. It's called Live Captions. I decided on Flatpak because it offered multiple benefits. One of which being is that it's available on most Linux distros. So it doesn't matter if you're running Ubuntu, Arch Linux, you can usually install Flatpak, you can enable the FlatHub repo, and you can just start using it. Another benefit it offers is sandboxing. So each Flatpak application has permissions, and it cannot use things that has not been granted permission to use. In the case of this application, it actually does not have the network permission. So you can actually rest easy knowing your data is not being exfiltrated to some other country because it's actually not capable of connecting to any external servers. So that's great. As for app compatibility, the speech recognition model, it runs locally on your CPU. It's compatible with most modern systems. So for example, I developed it on my home PC that runs a Ryzen 5 1600. So it's, like a first generation Ryzen. It's not the most modern CPU, but it runs fine. It can have issues with power throttling on some mobile devices. So right now it's running on my laptop, and if I were to put it into battery saving mode, this would not be keeping up right now. So it's just not as optimized as I would like it to be, but that can always be improved. So as for the features of this application, it has a built-in English model. It's not the most perfect. It may be making a lot of mistakes right now, but it's good enough, I would say, for some use cases. If you're watching a YouTube video, it can run really well. I will demonstrate some of the other features. So there's the option to load models and switch between them. So there are various models you can download. These are all testing models that I've made. But you can download them from this link, and you can add them from the local file system. Next, there's an option to toggle between capturing your microphone or capturing your desktop audio. So it's this microphone button. If you're watching a YouTube video, for example, you would want to keep this off so that it would capture your desktop audio. But in this case, I have it enabled, so it captures my microphone instead. There are some customization settings. You can change the font. You can show the text in uppercase versus lowercase. There's an option to fade text based on how confident it is that the word is correct. There's also an option to filter swear words and slurs. So, for example, right now I'm not planning to say any swear words, so I would rather keep this enabled because sometimes the model can make a mistake, and I wouldn't want something nasty being written here right now. There's also a history feature, so you can scroll through what you've captioned, you can copy the text, you can export it as a text file, you can, erase it, all that stuff. And there's also accuracy adjustment based on system performance. So depending on how fast your system can handle running the algorithm, it'll try to adjust how fast it's processing the audio such that it keeps up with real time. It does come at a performance trade-off, so you will see a little icon in the bottom right showing you that it's not keeping up right now. But it's better than nothing if your system can handle it at the correct speed. So, as for the speech recognition model, it was made possible by the next generation CalD project. The CalD project is an open source speech recognition toolkit, and the next generation version of that is basically CalD but upgraded with more modern model architectures. And it's based on the Icefall implementation of RNNT. So Icefall is part of the next generation CalD project. They have a bunch of training scripts, various recipes for different models over there. And I basically took one of those. The model weights are also based on a public pre-trained model they published. So I basically took that and one of their implementations, and that is what is being used right now. But I'm not using the raw model as it comes because it has a few limitations. So the pre-trained model does not support punctuation. It does not transcribe numbers as actual, numbers. It only does words. So for example, if I were to say 15,000, it would write it as words rather than numbers. And I decided I would try to fine-tune the pre-trained model in order to give it the capability to actually write the numbers and to write punctuation. But finding good data with that can be a big challenge. So what I ended up doing is I scraped a few thousand hours of videos from the internet, basically just random online videos. But the issue is they don't have captions. Well, some of them might have captions, but the quality of those can be questionable sometimes. And if I limit myself to just caption videos, then I would be shifting the data set distribution to something that might not match what you might watch on YouTube. So I took these videos without captions, and then what I did next is I ran them through OpenAI Whisper large model. So I basically used this model to make machine-generated captions for each of these videos. So I ended up with a couple thousand hours of audio. I had to, filter some of those for quality because the Whisper model is not perfect. It makes some mistakes. So I had to filter some of those out. For example, I removed all sentences that didn't have any punctuation in them and that kind of stuff. Now, an obvious question here might be, why didn't I just use Whisper in the first place? It's a pretty good model. It works great in this case. But you know, I'm going to talk about it a little bit. So it's an open source speech recognition model that OpenAI trained last year and released. It has pretty impressive accuracy. So it's based on a transformer architecture, which is similar to how large language models work. So for example, GPT. But its task is to convert speech into text. So it takes an audio as an input and it outputs text, or at least tries to. And the large model, it's basically on the scale of GPT-2. So some of you might know how well GPT-2 generated human-like text. It was state-of-the-art at some point. So it has that level of world knowledge, and it really helps it to generate captions. But the main limitation that prevented me from using it just in the application is that this architecture does not support streaming audio input natively, at least. So what is streaming audio input? So by streaming, I don't mean like Twitch streaming, although it is a similar principle. So when a model does not take streaming input, basically it has the capability to look ahead in the input. So when in this example, it's captioning this piece of audio, and it's trying to figure out what the next word is. It can look ahead of that, and it can look at future audio and figure out, what word makes the most grammatical sense here. So in this example, it figures out that the word "we" is the most correct one. And this is basically how Whisper works. It takes about a 30-second chunk of audio, and it figures it out on each chunk. But in the case of live captioning, we don't have a full audio input. We have what's called a streaming input. So in a streaming input, we basically don't have access to future audio frames. And the reason for this is because, they just don't exist yet. When you're watching a video, your browser, it's generating the audio as it goes. It's not downloading the full video at once and saving it, somewhere accessible to the application. So when we're doing live captioning, we basically don't have access to future audio frames. In this case, we are using the Pulse Audio API to get access to what's being played through the desktop audio. And we don't have access to what's, for example, about to play in 5 seconds. We don't have access to the full, video file that's playing. So for that reason, we have what's called a streaming input. So in a streaming input, the model has to figure out what to generate on the fly. It does not have access to, what's about to play in 5 seconds. So it's a more challenging situation, and this is what the model has to do. And the issue is that Whisper does not really support this kind of use case. You could try to coerce it into, you could segment the audio into a 5-second window that's shifting every half a second. Some people have done that, but it comes with an accuracy trade-off, and at some point it starts requiring a lot of performance. So for that reason, I decided it would be best to just train a model that, it supports streaming natively. So I would like to talk about how the model actually works, how you go from the raw audio signal to the text that's appearing right now. So the first step is to get the audio that we need to transcribe. So in our application, we're using Pulse Audio Server, and we basically ask, for the latest 3200 audio samples that's playing to this specific device. And it basically gives us this audio signal, but working with the raw signal can be a bit challenging. So a signal, an audio signal is just a bunch of numbers. In this case, it's 16,000 numbers per second. There are some signal analysis techniques you could try to apply, but what speech recognition researchers end up doing is they basically turn this problem into image recognition problem. And they do this by taking the Fourier transform of the signal to produce a spectrogram. So what we end up with is a much more compressed representation of the signal, and we can apply, image recognition techniques to this. And this is, the state of the art, I would say. So after we obtain the spectrogram, we can move on to the first neural network, which is called the encoder. So this is a recurrent neural network, which means it has a hidden state, and it uses this hidden state to basically form a memory of some sort. So, for example, in this case, it's probably forming a memory about, the speaker's, accent, gender, whatever helps it figure out an accurate output. So this recurrent neural network, outputs a hidden state, and this hidden state is used in subsequent calls to the network whenever we get new audio frames. And it also outputs this encoder vector. And we can use this later on to convert it into text. So the second neural network is called the decoder. It's a much more simple neural network. It basically takes the last two tokens, which are represented as integers. It has basically an embedding for each of those integers, and it performs some convolution on the two embeddings, and it outputs a decoder vector. And the next network is called the joiner. So the joiner basically takes both of these vectors and joins them. And this way it outputs a token probability vector, or logits, some people call it. I think it's useful to think of this vector as basically a list of probabilities. In this case, there's 500 elements in this list. Each value in this list corresponds to a specific vector based on its index. And the way we select which token to output next is basically to figure out, which token has the highest probability. So in this case, the one with the highest probability is number 2. It's the word "the" with a space at the beginning. And this is only one of the search algorithms that can be applied. There's different search algorithms where we don't take the most probable one at each step. There's beam search, but for simplicity, I'm just using greedy search, where at each step we just take the one that's most probable. And once we've picked this new token, we actually go back and we run the decoder again. This is because the last two tokens have actually been updated when we pick the new token. So we basically run this in a loop, essentially. And we run the decoder again. We reuse the vector that we got from the encoder. And we run the joiner again. And we get another probability vector. So at some point it outputs what's called the null token. So the null token basically means to break this loop and to basically wait for more audio frames to come in. What it really means is that there's no more tokens it can decode, and that it needs to wait for more audio frames to come in order to produce the next token. So the model just learns to output this token eventually. And once that has happened, we basically go back to the beginning. We wait for more audio to come in. We convert that to a spectrogram. We run the encoder again. You can actually avoid running the decoder again because the last two tokens haven't changed. We don't treat the null token as something we append to the last two tokens. So we run the joiner again, and this way, running it in a loop, we can generate text. And eventually, when we generate enough tokens, we get something that looks like this. So to convert this to actual text, we just join all the strings together. They contain their own formatting. Some of them start with a space, some of them don't. The model just kind of learns how to combine these in the correct way. This method of encoding tokens is called byte pair encoding. So It basically means that some of them have a space at the front, some of them don't. And we can just join them together to get a full string. Now, some of the things about this model architecture. So it has no static dictionary. It can output any arbitrary set of tokens. It can output words that it hasn't seen before in training. There's no like fixed list that it can only output. This was a problem with some older like open source speech recognition models, but this one doesn't run into that issue. Another thing is that it doesn't rely on like phonemes or what's called the alphabet. The model learns to output English text directly. In some older models, what would happen is we would try to predict the phoneme for each audio frame, and there would be some complicated set of rules to convert those phonemes into text. This one doesn't have that issue, and it can even learn to output punctuation, symbols, numbers, things that were much more difficult when you're dealing with phonemes. So another limitation this model doesn't have is that it doesn't have the requirement that each frame must output a single character, phoneme, or token. This was a problem in some older models as well. It's called what's called the CTC architecture. And one issue with this architecture was that if someone is speaking too quickly, you end up with the situation that there's multiple characters in a single frame, and the model just can't represent that correctly. It can only, output a single character, and it would run into issues, accuracy issues in that case. This model, doesn't have that issue because we run the decoder and the joiner in a loop, so it can actually output like multiple tokens for a single frame. So that's about it for the model. So to reiterate about the state of the project, so there's a functioning app you can download today. It has about 8,000 installs on FlatHub. The library is still in an early kind of state. There's not really any apps using it other than live captions. It is maybe somewhat of a niche use case because this is only optimal when you have, a streaming input. If you want to, generate captions for a video file or an audio file, you could just use OpenAI Whisper and you'll get better results that way because it can just look ahead in the input. So this library is only optimal if you have like a real-time streaming requirement like live captions does. And there's Python and C# bindings for this library. So if you're interested in messing around with it, trying to build something, you can definitely try using it. And as for the next steps of this project, so I would like to build Android voice input that's open source and runs locally. So one of the big issues with voice input on Android right now is that the only real option is like Google Keyboard, and it has the voice input thing, but what it does is it sends all your data to Google servers. Louis Rossman made a video about it, and it's just a privacy intrusion really, and there's no reason that it has to send all of that to some server somewhere. It can definitely run locally. So I would like to build voice input for keyboards that runs locally and doesn't intrude on your privacy. Some next steps for live captions specifically, given that I found a method that works for training the model, I would like to just scale it up. You can always just get more data, scale it up, train more models, better models. And I would like to explore more uses for live speech recognition. For example, when it comes to VR games, and most people use voice chat, but for deaf people it can be not really ideal. So you can find the application on FlatHub. You can get the library from GitHub. The library itself is published to the Python repository. It's also on NuGet, and you can mess around with it if you're interested. And that's about it. So if you're interested in the FUTO Fellowship Program, be sure to check it out on the FUTO website. You can just send your application. If you don't have an idea for a project, they have a list of project ideas that they would be interested in. Just send an application. If you're interested in this sort of work, they will take a look whether you're the perfect fit or not. There's no risk in sending the application. Thank you very much for watching this video.